the total number of surjective group homomorphism from the group Z20 to Z8. We know that number of group homomorphism, if F is a group homomorphism from Z20 to Z8, then we are seeking number we normally denote by hash symbol. This is number of surjective group homomorphism. We are seeking this one. If F is a group homomorphism from Zm to Zn, then number of 1 group homomorphism can be found by Euler-Toten function phi m if m divides n, and number of onto group homomorphism can be found by phi n if n divides m. There is no 1 group homomorphism if m doesn't divide n. Also, there is no onto group homomorphism if n doesn't divide m. This is the basic concept. So we are seeking surjective group homomorphism. It means that should be 1 and onto. It means that there is no onto group homomorphism because of 8 doesn't divide 20, so there is no onto group homomorphism. It means no surjective group homomorphism. So answer is mathematically option B. Let ZO plus be a group if the binary operation O plus is defined by if two elements A and B are coming from integer, then if we operate with this binary operation, then this give you A plus B minus 5 for all AB which are coming from set of integer. Now we are interested to find identity element of this group. ZO plus is a group and identity is unknown here. Then the property of identity, if an element, this is an element of the group, if A belongs to ZO plus, then A E is A. This is the property of identity, and there is nothing in this A and E. It means binary operation, and by the property of this or defining, this is A plus E minus 5 is A. Now this is the equation because of A, this A and E are elements of integer. So this is equation in terms of integer. So you can cancel out, otherwise you cannot, because of cancellation law hold whenever you can operate with inverse element of that. But we cancel out this by, as normally we do in calculation of just as in mathematics, because of these are integer. So minus E minus 5 is 0. This implies that A is 5, means identity is 5. So option D is correct. The rank of the matrix A, where A is this matrix. Now find rank of this matrix. So how to find rank of this matrix? And first we know that what is the rank. Rank is the greatest minor which has non-zero determinant. It means that, or in terms of non-zero rows or column vectors, this is known as rank. So first of all, row reduce this matrix and find number of non-zero rows. Apply row operation. We are changing R2 by R2 plus R1. Second is R3. We are changing R3 plus 4 times R1, and R4 is changing by as R4 plus 3 times R1. These are all operations we applying simultaneously to row reduce this matrix. So first row is same, minus 1, 1, minus 2, minus 1. Second row is 0, 0, again 0 and 0. Third row is 0, 0, minus 2 because of minus 8, so minus 4, and this one become minus 2. This is 0, 0, 3, 2 is 6, so minus 2 and minus 1. So you can say that these last two rows are in proportion. So you can do one thing, that divide this R3 by 1 upon 2. So this equivalent matrix is minus 1, 1, minus 2, minus 1, 0, 0, 0, 0, and this is 0, 0. You can take minus 1 of 1 by 2, 1 by 2, so 2, and this one will become 1, 0, 0, minus 2 and minus 1. Now apply R4, R4 change by R4 plus R3. So this row becomes 0 and this is also 0. So there is only 2 non-zero rows you got. So rank of this matrix is 2. Let T be a linear transformation from P to X to R square, and image of any polynomial under T is by order pair. P0 is first constituent and P1 is second constituent of the order pair. If S1 is this set 1x square and S2 is order pair 1001 with two bases of P2x and R2, these two bases are known as standard ordered bases, then the matrix of T with respect to bases S1 to S2. Always we find matrix representation with the help of bases, one from domain and second one from codomain. Here basis for domain is S1 and basis for codomain is known as S2, and this is nothing but order pair 1 0 0 1, and S1 for domain is 1x x square. This one help us to generate constant polynomial. This x help us to generate a linear polynomial and x square quadratic polynomial. 10 help us to locate elements on x-axis, and 01 help us to locate element on y-axis, and linear combination of these help us to generate any element in R square. So these are basic or generating set. So matrix presentation of linear transformation T from S1 to S2. Suppose this is matrix A. So procedure is that consider Px is 1 by 1, domain element is 1, then again Px is x, and after that Px is x square. 1 by 1 we consider Px as these elements of domain basis. After applying T on these, this T will send image of P as P0, because of this is a constant polynomial. So P0 and P1 is same. So P0 is also 1 and P0 and P1 both are same. So this is order pair. Write this image with the help of basis of codomain. So This is 1 1 0 plus 1 0 1. This is x, so T will send this as P0 is 0 and P1 is 1 because of identity polynomial. So this is 1 0 times 1 0 plus 1 times 0 1, and this one is last one is x square. So P0 is 0 and P1 is 1. So again this is 0 times 1 0 plus 1 times 0 1. So coefficient of this linear combination becomes columns. So 1 1 is first column, 0 1 and 0 1. So this is matrix representation of T, and size of this matrix is 2 by 3. Always if T is a linear transformation from, suppose this is a vector space V to W, then dimension of W becomes the row and dimension of V becomes column. So this is the fundamental concept to find matrix representation with respect to basis. Which one of the following is not a subspace of square matrices over R? For option associated, this problem is given as W3 is this set where trace of A is 0, and if A belongs to W2, then determinant of A is 0. In W1, first element is 0, and in W4, transpose of the matrix is same as given matrix. So we test these options one by one and reach the final answer. So for option A, in which a trace of A is 0, trace of A is 0, if this W3 will form subspace, then it will follow the all three's property of subspace test. As 0 matrix belongs there, means any square 0 matrix. Suppose this is 2 by 2 matrix, then this is trace of this matrix is also 0. So that 0 matrix belongs in W3. Also, if A is in W3, then CA will be in W3 because diagonal elements will increase or decrease by the same element C. So again trace will be 0 because of, you can consider if diagonal elements are A, B, C, D, and these diagonal elements are of A, then you can multiply these diagonal element by C, then their sum all again will be 0 because of distributive property. If we are taking two elements A and B, then their sum will be 0 because of diagonal sum. If A, B, C, D are diagonal elements, suppose 4 elements I have chosen, then their sum is also 0 and this sum will also 0. So sum of diagonal elements, when we taking sum of the matrices, then diagonal elements will become 0, means their trace will be 0. So option A is subspace. Now come to option B. As in option B, what is option B? In option B, determinant of A is 0. So 0 matrix is there is no problem. If we are taking two elements 1 0 0 1 0 0 0, determinant of this one is also 0 and determinant of 0 0 0 1 is also 0, but their sum is identity matrix of order 2, and their determinant of this matrix is not 0, means sum of two matrices is not in W2, so W2 is not a subspace, and we are interested only in which doesn't form subspace. So B option is a correct choice. Now let's see option C and D. If any element in W3 Then first element all first pivot position means A11 entry is 0. Then in 0 matrix first element is also 0 means in principal diagonal. In sum also, so W1 is also subspace. Now W3, now W4 means option D. So W1 is also a subspace. Now come to the point, option D. In W4 having the property A transpose is A means real symmetric matrix. Sum of two real symmetric matrices is again symmetric. There is scalar multiply by any scalar, real scalar, then it is also symmetric matrix. And 0 matrix is again symmetric matrix. So option D forms subspace. So correct choice is only option B, where W2 is not forming subspace. The group S3 cross S3 has an element of order, means possible order of an element which is in S3 cross S3. What? We know that this is a direct product of finite groups of finite product. In this, the order of an element in a direct product of a finite number of finite groups is the LCM of the components of the element. LCM of the components of the elements of this is equal to order of an element G1, G2 and so on up to Gn. If this is an element, then order of this element is LCM of individual or order of the components. We know that S3 has elements of order 1, 2, 3. So S3 cross S3 will have element. Suppose this is an element AB, then order of this element AB will be LCM of possible order of A and possible order of B. We know that possible order of A and B are means 1, 2 and 3 means 1, 1 LCM of this one, LCM of 1, 2, LCM of 1, 3 and 3 other pair also, LCM of 3, 1, LCM of 3, 2 and LCM of 3, 3. If and LCM of 2, 3, LCM of 1, 2 is done. If some LCM is remain, then you can justify yourself. But you can check here all LCM is either 1, 2, 3 and 6. None other than these LCMs. So possible order of this one element is 6. So option D is correct. LCM of an element which is in direct product of S3 cross S3 never be 18, 9 and other. So option D is correct. If the characteristic values of a 3 by 3 real matrix A are -1, 1 and 0, then which one option is correct? If characteristic values of a matrix as A matrix is 3 by 3 of the size and eigenvalues of this matrix are 1, -1 and 0. If eigenvalues of a matrix is given, then somehow at most or maximum information is given to us. If all eigenvalues we known, then we can write characteristic polynomial by x minus 1, x plus 1, x. This is the characteristic polynomial. So you can write chx, ch for characteristic, and this is in variable x. So I wrote x here. This is x square minus 1 x. So x cube minus x. This is characteristic polynomial. And by Cayley-Hamilton theorem, we know that every matrix satisfies its characteristic polynomial. This means that a cube minus a is 0. This means that a cube is a. Means option D is correct. Now, there is nothing to do in this problem if you know the correct Cayley-Hamilton theorem and how to write characteristic polynomial if eigenvalues are given to us. If lambda 1, lambda 2, lambda 3 are eigenvalues, then x minus lambda 1, x minus lambda 2, x minus lambda 3. Like this, we write characteristic polynomial. Let T be a linear transformation from R square to R square, and T is defining by this structure T of xy is x comma 0, then the characteristic values of T are. First, we find matrix representation of T, and T of xy is given as x comma 0. We know that basis for R square is 1 comma 0 and 0 comma 1. This is basis and these are constituents of basis. So write image of codomain with the help of these basis element and same as domain and codomain. So T of 1 comma 0 will be 1 comma 0, and this can written as 0 times 1 comma 0 plus 1 time 1 comma 0 and 0 times 0 comma 1. T of 0 1 can be written as 0 0, and this one can be written as 0 times 1 comma 0 plus 0 times 0 comma 1, means linear combination of basis element. So matrix representation of this one is none other than coefficients of this linear combination. Then characteristic values of this matrix representation as sum of all lambdas I is 1 and determinant of this matrix is 0. Means determinant is 0 means one eigenvalue is 0 compulsory. So option C and D discard here. But trace of this matrix representation is 1, and in option B trace is minus 1. So option A is correct because of trace is positive 1.